Okay, now I'm recording. Sorry about that. All right, so now I'm going to share my screen again. I just remembered that. All right, so briefly to summarize, we said that we've got a kinetic energy coming into the wind turbine. We've got a kinetic energy coming out of the wind turbine. The difference between those must have been converted into work. So we've got our differences in kinetic energy, and we know what the velocities are, but we don't know what the mass is. So that's kind of the big question here. What's the mass of the air that's interacting with the wind turbine? So to get the mass, what we're going to do is take the volume of this cylinder of air that is interacting with the wind turbine in 1 second, and then take that times the density of the air. And that'll get us our mass of the air that's interacting with the wind turbine in 1 second. And then we can plug that into here. All right, so we've got the volume of this cylinder. Take that times the density, and our meters cubed cancels out. So we get 966 kilograms. That is the mass of the air that is interacting with the wind turbine in 1 second. And now we can plug this into our calculation for kinetic energy. So our final kinetic energy is 1/2 times that mass times the velocity squared. And the exiting velocity, the final velocity, is 8 meters per second, minus the initial kinetic energy. We have 1/2 times that mass again. We don't lose mass as we're going through the swept area, so it's the same mass, times the initial velocity, which is 10 meters per second. And again, we square it. So we plug those numbers into our calculator. We get some big numbers and we subtract them. And we get negative 17,388 kilograms times meter squared per second squared, which seems like a weird set of units. But that's why I gave you the hint in number 1 to tell you that actually this is another definition of a joule. So this is nothing but negative 17,388 joules, or about negative 17.39 kilojoules. And we note here it's a negative number. Why? Because it says calculate the work done by the wind. So from the perspective of the wind, it's doing work. Work is leaving the system. And so therefore it's negative by our convention that we talked about last time. When something leaves a system, heat or work leaves a system, it's negative. When heat or work gets added to the system, it's positive. All right, so any questions about number 1? Okay, then number 2 is pretty straightforward. Number 2 says, what is the power input to the wind turbine in problem number 1? It's pretty convenient here because we calculated the work in 1 second. So all we have to do to calculate the power is divide by a unit of time. We may as well divide by 1 second because that's the amount of work done in 1 second. So let's just divide by 1 second, and then we get 17,388 joules per second because we're dividing by 1 second. And we know that a joule per second is just a watt, and a watt is a unit of power. So that's actually pretty straightforward. Nothing too complicated about that. So our answer is 17,388 watts, or about 17.40 kilowatts. Either one is fine. Notice here our number is positive. It's a positive number because it says, what is the power input to the wind turbine? So now our perspective is different. Now our perspective is the power coming into the wind turbine. So the power is coming into the wind turbine. So the wind turbine is our system. So that's going to be a positive number because it's an input. Okay, any questions about that? Okay, then number 3. Number 3 says that this is where I mentioned last time that this is like Thomas the Tank Engine, or like our steam engine. We've got a steam engine of some kind, and we've got a cylinder and a piston moving inside that cylinder. And the bore, that means the diameter of that piston or cylinder, is 20 centimeters. And the stroke, the distance that piston is traveling inside that cylinder, is 30 centimeters. And the inlet is connected to a steam pipe with a constant pressure, which is a big assumption, but it makes it a lot easier. So we'll say, for now, the pressure is constant inside that cylinder at 600 psi. Calculate the work done by the steam for every stroke of the piston. All right, so we're calculating the work. Remember that work is force times distance times cosine theta. So we got to figure out what those terms are. So what is the force? Well, it doesn't tell us exactly what the force is, but we talked about this equation in the first class session last Monday. And we talked about how the force acting on the walls of a cylinder, or really anything that where you have a pressure inside of some container, the force acting on the outside of that container is equal to the pressure inside that container times the area, right? So this kind of works out. The pressure is, for example, in pounds force per inch squared, and the area could be in inches squared. So the inches squared cancels out, and you're left with pounds force, which is a unit of force. So this is a good equation to have in your back pocket for problems like this. The force is equal to the pressure times the area. So what area are we interested in here? It's not the area of the cylinder walls or anything. It's the area of the piston. What is the area that the steam is acting on? It's the area of that piston, where it pushes the piston inside the cylinder. So we're going to use this equation to calculate the force that the steam is pressing on the piston with. That's the force in our equation for work. And then we need to know the distance in the equation for work. That's just the stroke of the piston. It tells us that's the distance the piston travels back and forth. So that is going to be our D in our equation for work. And then the last thing we'll have to think about is cosine theta. What is cosine theta? So we'll get to that in just a minute. All right, so that's what we're going to do. We have this arrangement. I find it helpful to do a little drawing for a lot of these. This is our arrangement where we have a steam pressure in here of 600 psi, and it's inside a cylinder with a diameter of 20 centimeters. And it's acting on this piston that is moving this way, and it's moving this way a distance of 30 centimeters. All right, so we need to think about our equation for work. Work equals FD cosine theta. So what is the F? That's probably the biggest calculation here. What is the F? Well, we know F equals PA. F equals PA. But what is the area? What is the area of that piston? So to do that, there's different ways to do this actually. You could convert into metric or into inches and then convert at the end. There's different ways that you could do this. But here I chose to convert into inches right away. So I converted the diameter into 7.87 inches and the stroke into 11.81 inches. And then I calculated the area from this equation, F equals PA. The area is pi r squared. It's just a circle. So the pi r squared, we take the diameter here, divide by 2, and then square it, and multiply times pi, and we get the area of this piston to be 48.64 inches squared. So now we can plug that into this equation, and we have our pressure, which is 600 psi, or 600 pounds force per inch squared, times our area, which is 48.64 inches squared. Inches squared cancels out, and we're left with the force of 29,184 pounds force. And now what I'm going to do, again, you can do it different ways, but what I'm going to do is convert into metric, because I know that if I take a Newton times a meter for the distance, then I'm going to get joules for the output. So I'm going to do it that way. So I'm going to convert that 29,184 pounds force into newtons. So there's my conversion factor, which was given in the problem as hint number 2. So I get my force on the piston to be 131,036 newtons. So there's the F that I'm going to plug into my equation for work. And the rest is pretty trivial. So here's my equation for work. Work equals force times distance times cosine theta. So here is my work, or excuse me, here's my force. Here was my distance. And I'm going to plug it in as meters because I know if I take newtons times meters, I'll get joules as an output. So I'm plugging in 0.3 meters as the distance. And then now I need to think about what is theta. Theta is the angle between the direction the force is applied and the direction of motion. And in this case, the steam is pressing on this piston directly in this direction. It's trying to push the piston to the right. So it's actually aligned. It's actually pushing in the same direction that the piston is moving. So the angle theta between those is 0 degrees. Angle is, it's not nothing, but it is 0 degrees. It's exactly 0 degrees. And if you plug in cosine of 0 degrees to your calculator, you get 1. So you're not ignoring this term, but as it turns out, it doesn't really affect the answer because that just results in 1. So you take your force times your distance times 1, and you get 39,311 Newton meters, which is the same thing as a joule. So the answer, because we're talking about the work done by the steam, we know that work is leaving the system. The system is the steam, so work is leaving the steam, so it needs to be a negative number. So our answer is negative 39,311 joules, or about negative 39.31 kilojoules. Any questions about that? Okay, and then number 4 is really similar to number 2. It says that it takes 0.2 seconds to extend. That process that we just talked about, it takes 0.2 seconds to happen. What is the power of the steam engine in horsepower? So first, let's just convert it to some unit of power. And we have our answer for work in joules or in kilojoules. So let's use that and divide by the number of seconds, because joules per second, we know what that is. That's a watt. So let's use that. We'll take 39,311 joules divided by the delta T, how long it takes. That's 0.2 seconds. And we get 196,555 joules per second. And a joule per second is just a watt. And so we get 196,555 watts. But that's not quite the final answer because it asks for it in horsepower. So no problem. They're both units of power, so there's just a conversion between them. And it tells us a horsepower is 746 watts. So we multiply times 1 horsepower per 746 watts. Our watts cancel out. And we get 263.5 horsepower, which seems somewhat reasonable for maybe a really old steam engine. I think probably the newer ones are on the order of thousands of horsepower, but maybe for a really old steam engine like Thomas, Thomas the tank engine, this might be somewhat realistic for an old tank engine driving around the island of Sodor, in case you're familiar with that show. All right. Any questions about that? There's a little note here, but that's kind of just a side note. Any questions? All right. So I did want to make just a quick note here. This will come back in a couple of class sessions. We'll talk more about this. And I just want to make a note here that really what we did here is assume that pressure remains constant. So we didn't say that pressure is reducing as the piston expands like it actually would in real life. But we made the assumption that pressure is constant, and then we took the change in volume. So that's actually another equation for work. The work is the pressure times the change in volume. Now, we haven't talked about that yet, but we will in a couple of class sessions. So really all you have to do to calculate the work, you have to take the area of this rectangle right here where you plot the pressure versus the volume. This is called a PV diagram, pressure volume diagram. And it's really convenient because you can calculate the work done by one cycle in this steam cycle by just calculating the area under this curve, the area in this rectangle. So it's actually pretty convenient. All right. If we were to make it more realistic and say, okay, actually the pressure inside that cylinder is not really going to be constant because the piston is expanding. So our volume is expanding. And as the volume expands, the pressure is going to decrease. So really, more realistic would be a little bit more like this, where you still have a PV diagram, pressure versus volume, but really what would happen is the pressure would decrease as the volume expands. But it's still true that the area inside here is the work done by one cycle in this process. All right, we haven't talked about that yet. I don't expect you to know that, but we're going to. So that's a little bit of foreshadowing to a few days, maybe 2 weeks or so in the future. All right, I will stop the recording